that, today we are now going to do question 4 of 2012. So we have a parabola and a circle with center 0, 2, just resting on the parabola. So let xy be a point on the parabola such that x is not equal to 0. Excuse me. So that the line joining this point to the center on the circle is given by this. So we are now going to draw a line from here to here. Show that the line, so the xy is a point on this parabola, and so this point is x squared, since y equals to x squared. Now the gradient m equals to rise over run equals to x squared minus 2 over x. There. So with the help of the result of part 1, show that the coordinates of B are given by this. So we need to find where m equals to negative 1 over x. So m equals to negative 1 over the gradient, which is 2x. So minus 1 over 2x equals to x squared minus 2 over x. So minus half equals to x squared minus 2. So minus 1 equals to 2x squared minus 4. So 2x squared equals to 3. X squared equals to 3 over 2, and x equals to the square root of 3 over 2. Since it touches the parabola, m is minus 1 over the gradient, which in this case is 2x by differentiating. So the minor arc and AB and the radius, and so since the x is square root of 3 over 2, we calculate it to be square root of 3 over 2, 3 over 2. Show that the area on the sector on the circle enclosed by the radius to A, the minor arc AB, and the radius to B is equal to this. Okay, so first let me clarify this a bit. There we go. So we are now going to write down the coordinates of each of them. So we're going to zoom in and write down the coordinates. So this is 0, 2. This is square root of 3 over 2, 3 over 2. And this angle just happens to be, so we need to find this theta. And theta, we'll put this here. Let's make this clear. Theta equals to sine inverse. Actually, we won't use sine inverse because we don't know the hypotenuse and we want to make it as simple as possible. So theta equals to tangent inverse. So the opposite is square root of 3 over 2. Again, I don't like this rationalized, but when I have 1 over the square root of 2, I would absolutely want it rationalized. So square root of 3 over 2 over half equals to tangent inverse square root of 6, and then you check it, it seems to be right. So the sector enclosed by the radius to A, the minor arc AB, and the radius to B is given by this. Great. So let me see. So show that the area of this sector. So the area of the sector is half. Area equals to half r theta. It's half r squared theta equals to half r squared turns out to be square root of 3 over 2. We use Pythagoras here. Half squared plus square root of 3 over 2 squared. Half squared plus 3 over 2 tangent inverse the square root of 6. We are going to use tangent inverse for now, but we are going to see why it is put in cos equal to 7 over 4 tangent inverse the square root of 6. Now we're going to convert the tangent inverse to cosine inverse. So tangent inverse square root of 6 basically means this is square root of 6, this is 1. And this is the square root of 7 by Pythagoras. And this is 7 over 4 cos inverse the square root of 7 over 7. Again, I like my denominators rationalized, or you could write it as 7 over 4 cos inverse 1 over the square root of 7. There. We are done. Suppose now that a circle with center 0 is resting on the parabola. Find the range of values on A on which the circle and parabola touch at two distinct points. So now let's see. Our point is x squared, and x squared plus y squared equals to r squared. So x squared plus x4 equals to r squared. And since x4 plus x squared minus r squared equals to 0. So we need to find the range of values where b squared minus 4ac, which you know is the discriminant, is greater than 0. So b is 1 minus 4, 1 minus r squared is greater than or equal to 0. So this means 4r squared is greater than -1. So r squared is greater than -1/4. But we can't do this. Find the range of values of A for this. So our y turns out to be, so we can't do this. Basically we can't, because I got the formula for the circle wrong, and so this actually turns out to be x squared plus y minus a squared equals to r squared. This video is getting a bit long because obviously this is taking very long. So x squared plus x squared minus a squared equals to r squared. So this means x4 plus x squared 1 minus 2a plus a squared minus r squared equals to 0. So find the range of values for A for which the circle and parabola touch at two distinct points. So we need to find the range of values where b squared minus 4ac is greater than 0. So 1 minus 2a squared minus 4 a squared minus r squared is greater than 0. So 1 minus 4a plus 4a squared minus 4a squared plus 4r squared is greater than 0. So we can cancel off the a squared, giving us a must be less than 4r squared minus 1/4. And since 4r squared is always positive, so this basically means that this a must be greater than 1/4. Yes, 1/4. So let r be the radius of a circle. This express a as a function of r, distinguishing between the case in which a circle is and is not in contact with the vertex of the parabola. Obviously the circle can't be in contact with the vertex of the parabola, then it will stay at 5. Yes, 5. Wait, I mean 3 distinct points. So now that a circle of center 0 is resting on a parabola. So m equals to x squared minus a over x. So m equals to -1/2x. Because we can change 2 to a, so basically I'm doing a generalized problem here. -12 equals to x squared minus a. So x squared equals to a minus half. And x squared plus y squared equals to r. So x squared plus x to the power of 4 equals to r. So let express a as a function of r. So we can substitute this. A minus half plus a minus half squared equals to 4. A minus half plus a squared minus a plus half 1/4 equals to r. So we can take away this and this. So a equals to square root of r plus 1/4. So express a as a function of r. Distinguishing between the cases. Well, obviously it can't be in contact with the vertex of the parabola because that's what I talked about. Anyway, well, see you in another MAT video.